My name is Jo Etzel, and I'm going to be talking about my paper for the OpenQC project called Efficient Evaluation of the OpenQC Task fMRI Dataset. And I have no disclosures. So there's that thing. So just in case you didn't fully read and memorize my paper, I wanted to give a bit of a introduction, because how we do QC is a little bit different than what some of the other groups did. But I believe it's very flexible and adaptable and works well. So I'm hoping that some of you might be inspired to use a bit, even though it's perhaps different. But with QC, context really matters for what the different groups have done. So I wanted to explain mine a bit. I'm a staff scientist in a large psychology lab. We're not doing software development. The main purpose of the lab is psychology research. And some of our fMRI studies that I've been involved with collect data for years and years and have full-time staff who are generally not very experienced programmers, whereas other projects are much smaller and the students or postdocs are doing them pretty much on their own. So I need methods that are going to work for kind of both sets of people. But pretty much the research of the groups I work with are pretty much all task fMRI data sets. So that's what I focused on here as well, including for this OpenQC project. I worked with the task data. So I'm going to talk, so while I did the task data set, I'll be talking about both task and image QC criteria, especially as implemented in the two knitrs that are released accompanying the paper. And knitr is a package for making automated dynamic reports. There's lots of different ways you can do this. I like R and LaTeX, then compiled to PDF. And one of the reasons I like this is for stability. It's been stable for a year, for a decade so far, and that's on multiple operating systems, lots of user changes, lots of version changes, but it has been proved very, very stable. Though for reproducibility, like most of these dynamic reports, and especially if you're compiling to PDF, you have to have both the plain text file, the RNW source, and the compiled PDF together. You can't just distribute the PDF by itself. But a feature of all dynamic reporting systems is that the code and the text parts of the report are together in the source file. And that's great because it preserves the link between the figure or plot or whatever and the code that made it. If you've ever tried backtracking from like an image copy pasted into Word and trying to find the image to make a modification, you know how painful that can be, especially if a few years have gone by. And another thing that I really like about knitrs is that we use them as kind of templates. So, and there's a few examples and some links for more details about how this goes. But what I mean by a template is that the source is written once by me or another more experienced lab member, but then it can be compiled a large number of times, for example, for every participant as they come into the study. And you don't need as much programming experience to compile the things as you do to make them, which is good for all of the different levels of people that need to use the files. But the source code isn't hidden. It's still in the template for those that do need to see the code to see it. Okay. So another little preliminary is that the OpenQC project is a special case in that it's already finished. So I just made 2 summary knitrs with all of the people in there together. Their group summaries, and group reports are great, to accompany a publication like I did here, but they are not what I want to emphasize, that you should not be doing that, holding off for the group if you have a study that's in process. during the data collection, the QC report should be made after every scanning session as quickly as possible. And here's an example of one from a study that's going on now. And this is one person with 9 task runs. And these are the temporal standard deviation of each of the 9 runs. And one of these is clearly not like the others. And the RA did spot it and let me know, because she was able to make the report quickly enough that we could find the bad run, talk to the physicists, and keep that run from getting into the analysis, because we don't want to be including that in our analyses. It's definitely not right. So that's what I mean by this efficient evaluation in the title, because what I have described and we'll be talking about today is reports that are kind of the minimal of what we need to be able to make them quickly and have people actually review them consistently, but not so minimal that we miss big problems. So it's definitely a balancing act. And your situation, what's considered huge and project wrecking level of problems may be different, or your folks may have more time to review all the files. But I do see it as a kind of a balancing act between what's feasible to include and what's just too much. So, okay. So getting into the reports, I'm going to start, there's 2 of them, one for the image relating criteria and another pair for the tasks. And going to start with the imaging one, and it has 2 parts as well. The first one about movement with the realignment parameters, and the second about the brain images. So getting started with the movement, this is what the top of the knitr looks like. This is our standard display for evaluating movement, and I'll kind of walk you through it a bit. It's a 2-part plot. We make one of these for every run. In this case, 1 subject, 1 run. So the top half is the realignment parameters, the XYZ roll pitch yaw. The second is the bottom half is the FD, framewise displacement. Okay, so the x-axis is time, TRs, in TRs. The gray vertical bars are 1-minute intervals. The little tick marks in between there are marking the onset of each trial. And then the red line is at the FD 0.9 mark, because that's what we're using for frame censoring, movement censoring. And then it has a text bar there written to say how many frames were censored. And that text would have been in red if it was above the threshold of 20% of the run frames censored, which is where we omit runs for too much movement. And in this case, no project participants met that threshold for having to have the entire run dropped due to too much movement. And the 0.9 threshold is high, higher than a lot of folks use for fMRI. And I wanted to explain a little bit more of why we're using that now. And well, this is a lot of the explanation, is that we have a lot of data sets that have extremely striking apparent motion. What I mean by apparent motion is that the oscillations here, this is respiration. This blog post and others have how I know why I'm so confident that this is indeed respiration, not actual head motion. But this is fairly typical for us. And, if we were using the 0.5 threshold for this participant, we would have to drop the run. It would have just about half the frames censored. And I really don't want to be censoring every single breath and having to drop runs because people were breathing. And also because the overt head motion, meaning actual moving of the head, is generally quite worse, I believe, for the quality and for analysis results than breathing and apparent motion. hopefully someday soon I'll write that up, ask me about it afterwards of why I think that's the case if I have time. Apparent motion definitely varies with acquisition parameters. If you have accelerated sequences, multiband sequences, you tend to see it more. But it also has to do with participant size, something about the head volume versus lung volume, that kind of thing. And their position in the scanner can matter a bit. Other factors probably as well that I'm not sure about. So this is, like I said, one run from a study. Here's another example from a different person, the same study in hardware. And this person has even more obvious apparent motion. In this case, even with, and I would say pretty much no overt motion at all. This is all breathing. And if we use the 0.5 threshold again, we would have to drop it. Even with the FD 0.9 threshold, it's pretty ugly. We're catching more of the breathing than I would like. But then here's a third person from the same study and same hardware and acquisitions and everything. And this person, you can see the little wiggly from the breathing, but it's a drastically smaller amount than the other folks. So I don't like using the fixed threshold of 0.9 because it's not adaptable to these different cases, but it seems like the least bad way to go about the censoring at the moment. And hopefully sometime we'll do something better. But for now, I just use the 0.9 threshold on FD for the task data set for the project. Though I think that 0.5 would have been fine for this data set, maybe even a bit lower. But a few examples of what the task folks look like on these plots. Here's number 12. This one probably has the most apparent motion of anybody in the task data set. It's, you know, nothing as high as what I was showing on the previous plot, but it clearly looks like the oscillations. This subject 29 and some others, I would say basically are mostly overt head motion. This doesn't look that much like breathing to me. It looks more like they were moving their head a little teeny bit. A lot of the participants are kind of a mix, like here where you can see the oscillation, but there's also some periods with overt head motion superimposed. And then a good share of the people in the data set are just very, very, very still, which is, of course, lovely. And I don't know how they do it to stay so still for so long. So, okay, that was the motion bit. And now the other part of the image QC knitr is for the actual brain images. And so here's some of what I made for the project data set. And this is temporal mean. And we usually plot temporal mean, standard deviation, and TSNR. I just show volumes here because that's what I pre-process the data to. If we were using surfaces, I highly suggest plotting those as well. And the aim here is to have a uniform display for all of the people and runs so that you can spot what's different. In this case, subject 10 is the difference, is clearly different. And like I was just saying, we want to have quick visual review is what I'm aiming for generally. So in this case, I have 3 pages of the compiled PDF for the 30. So the temporal mean images for all 30 people fits on just 3 pages. And that's obviously very condensed. And if something seems suspicious, I can't figure out usually what happened by just the pages that are included in the knitr. The idea is to try to highlight things that then should be explored outside the knitr, to look at more files. It's really intended to be kind of flagging potential issues, not showing absolutely everything that might matter. And looking at these people, other than, 10 is clearly a different shape. The other people, there's still a lot of variations. The dropout varies, the intensity varies, how well the front of the head was normalized varies a lot. There's a lot of differences. but we would actually, by our usual standards, accept all of these except for 10. And these are more or less aligned to the MNI anatomy template. There's not massive artifacts in the surrounds or anything. We would take these. And similarly, here's the temporal standard deviation page from the thing. And again, there's obvious differences in how clear these look, but we would accept these. And you might be reading this and go, what do you consider massive, Joe? These are pretty massive. Well, here's an example of what I do call massive. This was coil layer. The head coil wasn't seated properly. And like here are some more. These are kind of where the spatial normalization drastically failed. The brains are clearly not the right shape, or here they're not even centered. Here's some examples where there's like a chunk taken out of them. These are what I call massive. And it can be shocking how good these cases look in the GLMs if you don't catch them and they get all the way through the GLMs. But why do I think this level is okay? And this is something that I'm going to kind of highlight. There's a lot of caveats. Ask me later for some details. But one of the reasons is that we're talking about bold, and in my case, it's pretty much always spatially normalized, not subject space. So we have a lot of spatial imprecision built into the system. We're not expecting the voxel level alignment. And that's also, we analyze things at the parcel level. So that's further kind of reducing the amount of spatial alignment that I'm expecting. Another thing is that we're working with task data, which lets me set up positive control analyses. And again, this is more than I can cover here, but I've done a fair bit of looking at what level of quality of image does what to the analysis results. How much can we accept? And this is clearly trade-offs, and everybody's trade-offs are different. But for us, we aim to catch the biggest and let some of these others pass in order to not drop as many people. But it definitely could be reducing our signal specificity in some cases. So just a very brief note about the code. If you look at this is some of the RNW accompanying that's part of the supplemental for the paper. And the brains that I was showing on the page just now are NIFTIs, and they were made in the first code chunk here. And they have the fMRI fMRI prep pre-processed images. You can see the path here, derivatives, func, sub, blah, blah, are read in, and then they're turned into the temporal mean and standard deviations with AFNI commands that are there in the second part. And these are plain text AFNI commands. I'm calling it system, so it's calling out directly to the AFNI, compiled AFNI files. And you might be wondering about that because, I mean, there's AFNI wrappers even for R and various interface packages. And some of this I could certainly calculate mean on my own. I don't have to have AFNI do it for me. But I want AFNI to do it for me. And I do it this way for transparency, because if somebody needs to change the analysis or know what I did, and maybe they only know Python, they would have a pretty good chance of figuring out what exactly we were doing from this code, even without knowing much R. And also for stability, because wrapper packages change way more often than the executables do, or be platform dependent, all sorts of other things, badness that can happen. And also to use the standard that if I describe a complicated GLM in AFNI with AFNI commands or SPM commands or some other standard package, people are going to have a much better chance of understanding exactly what I'm doing than if I came up with my own implementation and did it with my own syntax. Okay, so now on to tasks. The task related criteria are in the task knitters. And there's two sections to this file. The two criteria are both in this one. Ideally, we would have determined the task QC criteria during like piloting based on what the point of the experiment was, what really matters, what the task timing is. But in this case, we don't have many task details at all. So I inferred and kind of came up with some from the bids events file. So that's not recommended. This is a special case. Okay, so the behavioral knitr is also mostly plots. And I'll kind of walk you through this a bit. Again, it's time along the x-axis with people runs along the y-axis. The gray lines again give the 1 minute interval. Here, the little plotting symbols, the bottom part of them are for the trial types, control or task in this case, with the location of the plotting symbol indicating when the trial started. The upper symbols, the red and blue ones, are for responses with what they were, when they were. The little tick marks are if that particular response was correct. And then there's some summary stats at the right. So what can we say from this plot then? Well, I can see that the first two responses, the first two trials, they didn't respond to at all. But then they started responding and just kept on it going. They were actually, all of the trials afterwards were responded to and were responded to correctly, because that has the sum of the number of left and right responses. And they answered 62 of the 64 trials, so they only missed those first two. And of the trials that had the response, all of them were correct, which is what I was just saying. So what can I say about the other participants? So here's the first 14 from the knitr, and it's clear that everything lines up perfectly. They didn't have any kind of like jitter or anything in the design. Nobody clearly did the task completely wrong. And most of the responses were accurate. Most people had there's an awful lot of people with a proportion corrective 1. So some of these people missed a few trials, as in like they didn't respond to a few trials, but pretty much people did very, very well. 11 of the people were perfect, no missings, no errors. But there's a few cases that are not quite as perfect or interesting. So subject 13 here, I picked them because they have the lowest accuracy of anybody. I mean, 88% still pretty dang good, but maybe for this task, it's not. Maybe the analysis requires higher accuracy. I don't know. But when we look at where, how many no response trials are there? Not that many. 56 of them have a response. And the incorrect trials and missing trials are pretty evenly distributed. They maybe got a little bit worse as the run went on, but it's not that bad. So I would usually consider this person a found it hard, but was attentive enough, likely case. This person 16 is rather worse. They had the fewest trials with a response, though pretty much all the ones they made were accurate, but they really are dropping off after the first minute, where they have more and more missing trials. And this is the kind of person we would generally consider probably was getting sleepy or daydreaming or something as the run went on. And 25 is similar, though they went a bit further before the responses really started to trail off. So by our criterion, both 16 and 25 would be dropped because they have too many no response trials. Okay, so just a quick note about this code. And the quantitative test. So what I was describing was kind of a mix of qualitative and quantitative. But since there are quantitative tests, the knitr has code in it to explicitly check if the trials, how many no response trials were there, how are they distributed, does it have the number of trials of each type that it should have. In this case, just by looking at it, I could tell that everybody should have 64, 24 control, 40 task. So the code explicitly checks for that and prints out these little true that everybody had the count that should, but then it's flagging these 16 and 25 because of the number of their no response trials. So that's to let us know that that needs to be investigated. Okay, so to recap a little bit quickly, I was talking about the dynamic reports that we use for QC, and with R and knitr, LaTeX, and PDF. And an important part of this is the templates. I hope if you look at the code itself, hopefully it'll be a little bit more clear how this works. But using these templates lets less experienced programmers be able to use the files, but still keeping the code accessible, easy to find, easy to modify for those that know it better. However you go ahead and implement it, don't reinvent the wheel. I strongly suggest that you use the most standard, stable programs that you can, even if it's a little bit less quick or less elegant code than you might hope. And don't try to fit everything into a single report. We found it works better to have reports be quick, fairly easy to skim, and then look at more detailed reports from other places, MRI, QC, whatever, if these summary reports flag things that might be important. There's no universal definition of efficient or even sufficient quality control. As I've been kind of saying, to me, efficiency is kind of a practical minimum level of QC testing. I want to have enough in the reports to catch the absolute biggest problems, but not so many that people don't use them or that they are not checked in a timely manner. I really want to be able to catch problematic sessions and big problems as quickly as possible. You know, what is a massive project wrecking problem is going to vary quite a bit, but I suspect that every single study or analysis is going to have something that would count as making the data set unusable. So I strongly suggest that you think about that and kind of, you know, what must be true about this data set, and then focus your QC there and make sure that you have that absolute essential part covered. And then you can adjust as needed if you find more problems, or if you find you have more time, can fit in more tests, adjust as it goes, but make sure you have the hugest problems covered and covered consistently. So thank you very much for your time and attention, and I hope that everything's going well with the conference.